Welcome. In this session in linear data analysis, we'll explore spectral clustering, and what we'll do is we'll try to find more than two clusters in a graph. So suppose that a graph has an adjacency matrix A. From that we can compute the degree matrix D, and then we can compute the Laplacian matrix, which we'll write as K. Suppose that there are n vertices. So what we know is that the nth eigenvector of the spectral decomposition of K is, that'll be 1 over the square root of n times the ones vector. And the Fiedler vector is n minus 1, and that has to be orthogonal to this vector, and so the dot product of those have to be 0. And that means that the sum, this Fiedler vector has to be a zero mean vector. And the idea is that we used previously was, what we did was we just took the positive and negative entries of this. Well, now let's consider, so this is a good one. Let's form a matrix, and we'll call it matrix 2. And let's suppose that what we do is its first column is the Fiedler vector, and its second column is that multiple of the ones vector. So this is an n by 2 matrix, and that means it has n observations. And once we use that word observations, what that means is that we could perform k-means clustering with k equals 2. Now, strictly speaking, we don't even need to have this, but for a notational convenience, I'll say, so what we've done is we've done the spectral decomposition, so that will be Q times lambda times Q transpose, and what we've done is we've taken the last two columns of this, and now we're going to treat it as though it's a data matrix, and we can perform k-means clustering. So this will be robust, and so this will be numerically robust. So robust numerically. Let's put a comma in there. And this would be our preferred way of performing the clustering, because there are these little annoyances with Fiedler vectors that sometimes we get 0 entries and we're not sure which way to put them. And a k-means clustering algorithm will pick that out quite nicely for us. Now, let's suppose we have a singly connected graph. That is, there's only one single component in the graph. So now, let's suppose that, so we'll suppose that our graph G has k clusters, and we'll be specific, and one component. So a component in terms of a graph is, it's how many things are connected to. So it's not like there aren't two little or more little islands in the graph. They're all somehow interconnected. So now what we'll do is we'll consider this. Let's consider forming E sub k, and it's going to be a lot like this. What we'll do is we'll start building it from the right side. So what we'll do is we'll put in that last one, even though we don't strictly need it, and then we'll put in the second last one, which we called the Fiedler vector, but now to us it's just another eigenvector. And now we can keep going, and we can keep filling into the right until we get to Q, and so that's going to be n minus k plus 1. And now what we can do is, so EK is a matrix that has all real entries, and it will have n observations because there are n vertices in this graph, and it will have k columns. And now what we can do is we can perform k-means on E sub k. And this is not a guaranteed algorithm, but if we're doing data analysis, it's one of the ways that we want to try. We want to try clustering our data just as data, and then we want to try converting the data to a graph, and then do clustering on the graph. And empirically, we'll find out which method works better. So let's erase all of this and go through a computer-generated example. Now, suppose that we're given a graph that has 30 vertices and we're told that 3 clusters are inside this graph. Suppose that we use a Cartesian grid to plot it, and so what we'll do is we'll have a grid that has 6 rows and 5 columns, and these are the connections. So we can see immediately a few things. For example, vertex 27 and 28 have no connection, 28 and 29 have only one connection, 30 and 29 have no connection, but so we know that some of these, are they in the same cluster? Are they in different clusters? We really don't know. So it's very difficult for us to visually spot clusters. Now, suppose that what we do is exactly what we did before. We form the adjacency matrix, and we form the degree matrix, we form the Laplacian matrix, we find its spectral decomposition, and now we'll take the last 3 eigenvectors and we'll treat those as data and perform k-means clustering. And when we do, these are the clusters that we find. So it's the same data as was plotted in the Cartesian coordinate frame, but now what we've done is we've changed the way that we're performing our plot.